what I'm going to do is put in a simple data set into Jamovi that I'm getting from the Oxford Handbook of Medical Statistics, but it actually originated in a Handbook of Small Datasets by David Hand. And David's going to have got his set of data from actually a scientific paper. So what I want is to put in some data of beta-thromoglobulin excretion in 12 healthy and 12 diabetic patients. So how do I want to set up this data? I've got these particular columns. So can I label them? Add variable. Computer variable, whatever. No, that's fine. Let's put in variable 1. Let's just put in whether they're healthy or not. So 1 for healthy. And I need 12 healthies. Whoops. How many have I got? 9, 10, 11, 12. And I'll put 0, actually let's put 2 for diabetic. So group 1 and group 2. Not being. So this is our coding. It doesn't matter how you code it, just so long as you know what each of those different codes means. Next we want the actual numbers, which I'm going to take out of the book. So you see that each column represents a variable, and then each row represents a participant in the study. These seem to have been ordered in height from smallest, they've been ranks already from smallest to largest, because this was a set of data for doing a ranked comparison. Because the data is not normally distributed. Now in general, your data you can assume to be normally distributed unless you have very strong reason to think it isn't. The reason for this is how the normal distribution arises because of what's something called the central limit theorem and the law of large numbers. Two fundamental things on how statistics works. So if you have any value which is made up of lots and lots of separate little contributions, some of which can be positive and some which can be negative, some can be large and some can be small, then when you add those up and they sort of average out against each other, they will generate a normal distribution. So in general, we see normal distributions all the time, which is why it's called normal, though it isn't normal, and probably calling it Gaussian is a better idea. So here's the data set. I like Jamovi because it has figured out that this thing should remain having this symbol beside it, because this thing is only has two particular values, two particular levels, and so it's a nominal variable, so it's diabetic or healthy. Whereas this one is a measure variable because it's quite clearly got things with decimal places and it's a continuous variable. That's nice, I like that. Jamovi manages to do those things very well. Oops, let's have a look at the data with a setup. That's better. I was wondering how I could do things. So setup, I need to say what I'm measuring in that particular one. And foolish me, I've closed the book so that I now can't find the particular one that I want to do. Wilcoxon, 2 sampled. So what I'm measuring there is beta Beta-Thromoglobulin Excretion. Oh, so B is already in the right place. Beta-Thromoglobulin Excretion. I should put in the units too. That's very bad. That's exceptionally bad because they're not giving me the values. What's the actual... so it's urinary Beta-Thromoglobulin Excretion, and they haven't told me the units. This is bad. So we'll put that in bad practice because it's forgotten to put the units in. I will go and find what beta-thromboglobulin units should be measured in by looking at beta microglobulin test. Beta microglobulin, oh, that's a different beta thing for our beta-thromboglobulin. Beta-thermoglobulin. Here's a paper with examples from the journal Blood. Here's the PDF. Wonder why I did that and hashed out. That's nice. I will download this to save for later, so that I've got some next work. So measurements. So it's nanograms per litre. Both plasma BTG and geometric mean. Oh, they used a geometric mean. Very interesting. Wonder why they did that. Sensitivity is that urine BTG was between this and 58 nanograms per litre. Sensitivity this, specificity. Now, bearing in mind these numbers and the size of them, and usually it's between 0.3 and 3.1 nanograms per milliliter. I'm thinking that that's going to be nanograms per litre. Well, actually, probably not. It looks like they're completely made up values, because they don't look to be particularly sensible. Values. And interestingly, it's associated with deep vein thrombosis. Okay. In that case, so possibly, roughly, let's call this nanograms per litre, because that probably is the right sort of scale, which is fine. Let's look at that variable. Set up. So variable A, they say is nominal with two levels. So I'm going to put it as patient status. We've got level 1, which is healthy. Well, yeah, we'll put healthy. I'm going to put normal because normal has different things. And level 2 is diabetic. So they are represented by the numbers 1 and 2. That's all good. That came out as a nice, easy way of calculating things. So there, I've got my data set up. So now I can actually do the statistical test by going to analysis. So I can do, it's there. Well, It's a variant of the t-test, so it is an independent samples t-test like thing. Now, because it is not normally distributed, actually let's go back again and look at the data and the setup. So delete that column. Yeah, don't need column C. Now let's do some analysis. Now I've got it nice and neat and set up properly. So where I got it out of the textbook, they were going to do a Wilcoxon 2 sample signed rank test, which you can't actually do within Jamovi. But if I go to independent samples t-test, that's what I would do if the data was normally distributed. If I'm assuming it's not normally distributed, then I'm going to do the Mann-Whitney U-test. I can compare it actually to the t-test just for interest. And to be honest, you should always be doing the Welch's version of the t-test and not the student's version of the t-test, because Welch's is a lot better. Welch's was introduced in the 1930s. There's no reason whatsoever to still be doing student's version. Right, so the dependent variable, the variable you're measuring as the outcome to see if anything is happening, is urinary beta-thromoglobulin excretion. The grouping variable is patient status. That's the thing that divides it into two groups, treated and untreated, healthy and unhealthy. However you're going to divide your data, it has to be in two groups. That's those two. I'm just going to put on the QQ plot to show the assumption test. So that is the thing about testing for normality. I can also put on the normality test itself to see if it's not normally distributed data using a Shapiro-Wilk test. I'm not a great fan of the normality tests and these ones. So if you got a p-value below 0.05, then your data would not be normally distributed. So to be quite honest, this data is normally distributed and there was no reason for doing the Wilcoxon's test at all. You could have done the student's t-test or the Welch's t-test. Do I want to look at the effect size? Probably not. What happens if I click on descriptive plots? I should have two box plots, or bar and line plots, showing me the difference between the two groups. And there's significant difference between the healthy and the diabetic group in where you find their numbers. So actually, Jamovi's given you the output and interactive. So I can, if I switch these off, or I can leave them on. So that's a lot better than SPSS, for example, where you get all of the different outputs and you keep having to run it over and over again to see what happens. So I can look at what happens if I put the effect size on. So it says the effect sizes here are minus 1.381, minus 1.381, 0.7431. So this one has a smaller effect size than the ones where I'm doing tests based on normality being assumed, the t-tests. So this is a weaker suggestion that there's a difference between the two, though it is still very strong. So values in the effect size of about 0.3 or a smallish effect, 0.5 plus 0.7, that's a medium mid effect, over 1 or below -1, that's a large effect. So from the t-test and Welch's I'm getting a very large effect, and from Mann-Whitney I'm getting a good size effect, a mid-size effect, but not absolutely enormous. I can also check for homogeneity of variance between the two different groups. Is that true? No. So they don't have equal variances in the two groups. So that is the probable reason why they went to using the Mann-Whitney U-test. Because if you've got unequal variances, the student's test breaks down. But Welch's test is perfectly valid. Oh, and it also tells you that their effect size is calculated as Cohen's d, which is good. So you can look up Cohen's d and see what those different effect sizes mean, whereas this one is a different calculation, so it's not really directly comparable. Right, let's look at the statistics. Students t-test, test statistics minus 3.384, relatively large. Anything above 2 is pretty big. Degrees of freedom 22. That is the number in your first group minus 1 plus the number in your second group minus 1. So 11 plus 11, 22. And you get a p-value of 0.003, so it's highly significant difference between the two groups. When you do Welch's, which corrects for having unequal variances, which we tested with this homogeneity test, Levene's test, you find that you have the test statistic is exactly the same, but the degrees of freedom change because there's a very complicated formula used to calculate that based on the ratios of the two different variances between the two different samples. So the p-value changes very slightly to being 0.004 instead of 0.003. And for Mann-Whitney, what you do is order them in the two in from smallest to largest, and you figure out how many of the smallest ones are in group 1 and how many of the largest ones are in group 1. Then you figure out how many of the smallest ones are in group 2 and how many of the largest ones are in group 2, and you figure out the differences in the ranks between the two groups. In this case it turns out to be 18.5, which has a very low p-value, so it's very significant in all of the different tests.